I would like to rewrite everything in terms of power 4 because we already have this power of 4 to the 1 power multiplying the x. So, and at the same time, I'm going to use that same law of exponents to write this as a 4 to the x times 4 to the first power. And this 16, I'm going to write it as 4 to the second power to the x power. And well, so that minus 3, of course, that remains the same. And well, so there's a couple of things that I would like to do. So coming back to analyzing the law of exponents that says a, oh, come on, a to the m to the n, in which we multiply the powers. That is, when we have the power of another power, we multiply the powers. Well, in this case, because this operation is multiplication, we know that multiplication, it's a commutative operation. That is, we can multiply m times n, or we can also multiply n times m in whatever order we want. All right? So I'm going to interchange these two exponents here. 4 to the x power to the second power plus 4. I'm going to write this 4 to the first power times, in the reverse order, just 4 times 4 to the x power. And I'm just going to put parentheses. And if we will, we are going to have a power 1 minus 3 and equals to 0. And I think from here we can see that quadratic pattern actually. Well, here is where we are going to send this problem to the world of u, in which we're going to say u equals to 4 to the x, that's a u squared plus 4u minus 3, and solve this equation. All right, let's see. So let's figure out what method we can use to solve this equation. Let's see if factoring works. Well, are there factors of -3 that add up to +4 perhaps? And I don't think it's going to be the case. If this one were a positive, well, +3 and +1, 3 times 1 is 3, and 3 plus 1 is 4. But it's not the case. We want the negative. So the only possible factors of -3 are -3 and 1. And in one case, we get as a result of addition, -2 or +2, not the middle coefficient. So in this case, we are going to use the quadratic formula. So let's go about it. So in this case, this is 1, well, a equals to 1, b equals to 4, and c equals to -3. We need those three quantities to use the quadratic formula. So x equals, let me use a different color actually. X equals to minus b plus minus the square root of 4, or b squared, minus 4ac, the whole thing divided by 2a. Well, in this case, minus b is -4 plus or minus the square root of 4 squared, minus 4 times the quantity a, which is 1, -3, which is the quantity c. All this madness inside of the radical, and that whole thing divided by 2a, which is simply 2 times 1. I'm going to continue over here. And well, so that's actually, okay, 4 squared, that's, well, number 1, -4, plus or minus the square root of 16 plus 12 over 2, which adds up to 4 plus or minus the square root of 16 plus 12, that's 28. And yeah, this is going to give us some funky numbers actually. So we need to simplify this to lowest term. So that square root of 28, we'd better simplify that by using one of the properties of radicals, you know. So we can use the square root of a times b. That's the square root of a times the square root of b. And for our particular case, the square root of 28, it's going to be, well, we can factor out the number 28 as a number that is a perfect square times whatever number. It doesn't have to be a perfect square. All we do ultimately is leave that result as whatever square root of the number is times the remaining radical. And well, 28 happens to be 4 times 7, the square root of 4, which is 2, the square root of 7, which is the square root of 7, and we'll leave it like this. All right. And what's next? Next is to just rewrite this result. That's a 4 plus or minus 2 root of 7, and divide whole thing by 2. All right, at this point we may keep dividing out or distributing or splitting up the fraction, because it turns out that both 4 and the coefficient 2 are divisible by 2. So let's go ahead and do that. So 4 divided by 2, that's 2, plus or minus 2 over 2, root of 7. All right. That means we are, yes.
Would the 4 be negative?
Which one? This 4? Oh, it's plus. Oh, yeah, this 4 you mean, right?
Yes.
Got it. Thank you. Yes, and that still remains negative. All right, that means we're going to obtain two different results. Number one, negative 1, and then a positive 1. So let's see what I got in my notes, right? Well, you know what? Let me keep this in terms. Oh, by the way, hold on. This is not x. This is not x. This is actually u, because we're solving the problem in the world of u. We're not back to the world of x actually. So let's see. So in this case, since u equals to negative 2 plus minus the square root of 7, well, so I'm going to go back to the world of u by back substituting for u, which in this case we said 4 to the x power equals negative 2 plus or minus the square root of 7. And again, there's a bunch of ways to solve this baby equation for x. So this is an exponential equation, because we have the x on the exponent of this constant value, this number. So we can take the log of your favorite base. It could be log base 10, it could be ln, it could be log of the same base 4 to cancel it out at once. However, I'd rather use ln, because in this case, if we use log base 4, and if and for some reason we don't have access to a device that actually evaluates logarithms of a different base other than 10 and e, well, we're doomed. So I'd rather just do ln, and well, smack down the x ln of 4 equals ln of negative 2 plus or minus the square root of 7, and x equals ln of negative 2 plus or minus root of 7, and then the whole thing divided by ln of 4. So from here we are going to obtain two different results. Number one, on the one hand, x1 equals ln of negative 2 minus root of 7, the whole thing divided by ln of 4. And the second result will be x2 equals to ln, clear this better, ln of negative 2 plus root of 7. And then the whole thing divided by ln of 4. Now, let's have a look at these two results more closely. What about what about x1? Would that be a legit solution? Why not? Right? Well, so negative 2, and then keep subtracting to make it even more negative, so we cannot take the logarithm of a negative argument, so we can ditch this result. All right? But what about the next one? Well, whatever that is, well, I actually have the result in approximate form. So that's actually approximately, I have negative 0.3155. So, and again, when we're solving this kind of equations, we want not just the exact solution, but also an approximate solution. And most of the times, the rule of thumb for exponentials and logarithmic equations and calculations and evaluations of functions, we go at least 4 digits, unless otherwise stated, which could be the case. It could be the case that maybe 5 digits, 7 digits, and the like. All right. But again, how are we going to know that? Well, most of the times our what's it called? This I forget the word anyway. When we're working on the homework, those blank boxes to fill in the answers have the instructions next to it in smaller letters, instructing how many decimal digits to use in our answer. So just stay sharp on those. All right, let's look at another one. So, okay, let's see. So for this one, what do we have? Log base 9 of x plus 3 log base 3 of x. And that equals to 14. Now in this case, we need to be very careful because it looks like we can do the following. Basketball, the exponent, and then so log base 9. No need to write this yet. Just log base 3 of x cubed, and then combine this into one single log. Log of x times x cubed equals 14. But there's something wrong over here. I can't use the product rule, right? Why not? Different bases, right? Ultimately, the question would be, what base do we keep? And well, no, it's not like we get to choose from the base. No, it has to be, everything has to be in the same base. Well, so we're going to use indeed a combination of the two rules. Let me write them down. So log base a of m plus log base a of n, come on, equals log base a of mn. That's the sum to product rule, okay, or the product rule simply. And we will also have to use the change of base formula when we have something like looks like log base a of some weird base of whatever quantity. We can come up with a new quantity or with a new base, log base b of x over log base b of a. So we introduce a whole new base to make the logarithms look like the same base. So we can use the previous property here, which in this case it's going to be the addition to product. You'll see how's that going to work. Well, I mean, we could go about, let me think about this. We could go about changing both to ln's. However, I would like to take advantage of the fact that these bases 9 and 3 are related by the fact that 9 is a power of 3. So I'm gonna leave this second term untouched, and I'm just gonna work on the first term. So what I'm gonna do here is rewrite log base 9 as an equivalent with an equivalent expression on a base 3 instead, so we can combine them all together. All right, that being said, so let's go about using that change of base formula and write this as a log base 3 of x over log base 3 of 9. All right? So essentially introduce a new base and write a quotient involving these two quantities here, the argument and the old base. And that plus 3 times log base 3 of x equals 14. So it looks like we're getting somewhere. And well, if it looks a little funky here, well, check this out. Check the quantity in the denominator. It's actually a nice number despite the notation, despite it looks in terms of weird logarithms, of weird bases. And that's because, check this out. The denominator can be rewritten, because we have in the argument, we have the number 9. So we can write that number 9 as a power of the exact same base, so to have a match and cancel them out, all right? So log base 3 of 3 quantity squared. So that's That's the equivalent form to write it down. That's times that, plus 3 log base 3 of x equals to 14. Okay, so let's simplify this right here. And let's see. We can divide out, or not divide out, actually cancel the logarithm with the exponential because the logarithm and the exponential bases actually match. So that's going to leave us with, what's that? Log base 3 of x divided by 2 plus 3 times log base 3 of x equals to 14. And well, so in this case, we're almost there to combining like terms. However, I don't want to combine a half plus 3. I think I'd rather work with integers instead. So what I'm going to do here is multiply both sides by 2. We can do it the other way around. A half plus 3, I think that's going to be 7 halves, I think, right? But let's do it in a different way. Let's just distribute, cancel here. And that's going to give us simply, let me continue here. That's log base 3 of x plus, when we distribute here, that's 2 times 3, which is 7 log base 3 of x equals to 14. No, not 14 actually. That's actually 28. All right? And where did I get the 7 from? Forget that. Yes, I think I was going one step ahead. So that's a 6. And that turns, yes, well, that's the 7. 7 log base 3 of x equals to 28. And well, let's isolate the logarithmic term. We're one step ahead. We're one step away to get that logarithm solved by dividing both sides by 7. And we'd better do this. I know there is another way to go about this, like basketballing the coefficient. That's going to leave us with some weird seventh degree equation when we get rid of the logarithm. So although it's doable, let's just go easy with it. So that is divide both sides by 7 and check the numbers that we're going to obtain in the end. Really nice numbers. Log base 3 of x equals 4. And well, we finally got that baby logarithmic equation. Exponentiate both sides on the base 3. That's going to cancel the log and the base. X equals 3 to the 4th power, which is 81. All right. Let's see what's next. Okay, the next one is going to be a similar type of problem. However, it's going to be a little funkier than letter D. Letter D had like really nice numbers, really nice bases, and it had convenient bases for which we were able to rewrite these logs in terms of a logarithm of the same base. However, well, that happened because the base of the first log was a power of the base of the log in the second term. So that's not the case, unfortunately, for letter E, because if we observe these two terms, log base 7 of x plus log base 6 of x equals to 1, the number 7 is not a power of 6, so we're in trouble here. Yes. However, we're going to use this change of base formula again. That is, I'm going to do ln this time. ln of x over ln of 7 plus ln of x over ln of 6. And that equals to 1. Well, so you might want to combine these fractions together. However, I'm going to do this by multiplying by the least common denominator on both sides. Well, so, and it turns out that the least common denominator will be the product of these two numbers right here. In the same way that you added, fractions like x over 7 plus x over 6 equals to 1. multiply both sides by the product of these two numbers, which is 42. 42, well, in this case, it's not going to be 42. I'm just going to go with with a product of logarithms. So essentially, we're going to do something like this. However, with logarithmic numbers, that is ln of 6 times ln of 7, ln of 6 times ln of 7. And well, when we distribute over the first term, see how the ln of 7's cancel? And that's going to leave us with ln of 6. Well, you know what? Let me write everything down. ln of 6 times ln of 7, ln of x, over ln of 7. Plus, do the same distribution over the second term. And that's going to leave us with the product of three logarithms. That is ln of 6 again, ln of 7, and ln of x. And the whole thing divided by this denominator we had from before, which is ln of 6. That equals to, do the distribution on the right hand side, 1 times ln of 6, ln of 7. Well, so that's ln of 6. Whoops. Times ln of 7. All right. So let's cancel or divide out common factors. On the first term, for example, we can divide out those two ln's of 7. On the second term, we can divide out those ln's of 6. And that's going to leave us with the following. ln of 6, ln of x plus ln of 7, ln of x equals ln of 6, ln of 7. Okay. What else? Well, so we do this in a way because ultimately our target is the x. So we don't have any x by itself. However, we have an x embedded in a logarithmic function. So in the meantime, what we're going to do is see what's going to happen here. Check this out. So this ln of x, notice how it is a common factor on both terms. So what we're going to do here is to factor it out. Factor out the ln of x. That's ln of 6 plus ln of 7, which is equal to ln of 6 times ln of 7. Okay? And well, we are about to get the ln x by itself by dividing both sides by this madness right here, ln of 6 plus ln of 7. ln of 6 plus ln of 7. All right. And well, I like this problem for a big reason, to show you to actually talk about a very common mistake when we're working with logarithms. And well, you'll see what I'm talking about in a second. So that's we can cancel this out. That's going to leave us with simply, let me erase this part. That was just like the analogy to go about this part. And let me go over here. ln of x equals to ln of 6 ln times ln of 7 divided by the sum ln of 6 plus ln of 7. And be careful, because the quantity in the numerator and the denominator, those two quantities look like using the properties of logarithm. However, this is one of those good examples to show you how not to use the properties of logarithms. So the denominator, that's a sum of logarithms, and when we have the sum of two logarithms, we can write it down as a one single log, ln of 6 times 7. That's not the case for the product of two logarithms. The product of two logarithms is just, it's only the product of the two logarithms. So ln of 6 times ln of 7. Okay, how about we verify that using the calculator? Can we go back? And when it opens, so ultimately In the end, this will be ln of 6 times ln of 7 divided by ln of 42. So let's see. Let me do. Okay. Correct. ln of 6 plus ln of 7 equals ln of 6 times 7, which is ln of 42. Incorrect. That's ln of 6 plus ln of, times, not plus, ln of 7 equals ln of 6 times 7. This is not correct. This is not correct. So let's use the calculator to show that. Okay. So that's ln. I'm going to go about ln of 6, close parentheses, plus ln of 7, and close parentheses. And I'm going to get this number, 3.73766, and many numbers, many digits, versus ln of its equivalent in this case, its equivalent value, that is ln of 42. Same result, all right? That's because we did the correct use of the sum to product rule of logarithms. Now, what about ln of 6, close parentheses, times ln of 7, close parentheses? Would that be the same as the addition, as the weird addition we did before in the incorrect statement? Well, let's see. No, it's not the same result. It's kind of close, but not quite. If we were doing the correct use of the properties, we should have obtained the exact same result without any variation at all. All right. However, notice the difference even by a decimal. The minute it differs by a decimal, that means this is not the correct use of the property. So just wanted to, so that was the purpose of this example right here, to show you how, oops, let me move it. Instead, let me move it somewhere else, to show you how this is not supposed to be done. All right? So, that being said, how about we get rid of the ln by simply exponentiating this whole madness on both sides. That's going to be x equals to e raised to the ln of 6 times ln of 7, the whole thing divided by ln of 42. And well, that's the exact result we want to obtain, as well as the approximate result, which according to my notes, to my calculations, is 2.5417. And that also being rounded to 4 decimal places. All right? Let's see what's next about this. Well, oh, the next one, it's pretty interesting because it's actually, so letter F. You may have seen this, you may not have seen this before, but maybe, okay, how many of you took AP Calculus in high school by any chance? Do you guys remember hyperbolic functions? Like sinh, cosh, tan? Okay, you might remember these functions that are sort of trigonometric functions, but no, they have an extra h. So let me do some notation. So like sinh x and cosh x. Well, you might remember back then in AP Calculus that trigonometric functions, as opposed to hyperbolic functions, well, trigonometric functions are functions of angles, and those are periodic functions, because we go about, or we go around the circle and fall again in the same point after we add 360 degrees or 2 pi, depending on the system we're working. However, these hyperbolic functions which have the form of trigonometry, because there it is, the sin, the cos, And well, in this case, but this because of this h, that's something else. Those were defined as functions of exponential in terms of exponentials, not as functions of angles. That is, and you might remember these identities: e to the x minus e to the negative x over 2, and e to the x plus e to the negative x over 2. If you haven't seen this before, don't worry. You're not expected to know this for this class. We actually, when you get to calculus 2, that's the first thing we cover in Math 151 in Calc 2. So, but I wanted to make this relation to something you may have seen before. And so when you look at this equation, hey, that looks kind of familiar. And well, essentially we're solving the equation. Cos x equals to 3. Well, which is kind of a weird kind of equation that we need to rewrite in terms of its definition in exponentials. And well, we don't need this anymore. Just wanted to take a little side trip here. And well, let's go about this equation. So number one, again, regardless of where is this equation coming from, hyperbolic, trigonometric, etc., well, we're now working on an exponential equation. And this is an equation that contains more than one exponential, not just one exponential that we can easily isolate and treat it like a baby equation. No, it's not going to be one of those. So we will have to do some algebra here. Well, number one, I would like to solve for the exponential terms here. So let's multiply both sides by 2. And that's an e to the x plus e to the negative x equals to 6. And well, it looks like we're doomed here because we cannot add these two exponentials together. And the reason to this is that the exponentials are not the same. Had they been the same, well, we can easily combine them, you know, e to the x plus e to the x, it would have been e to the 2e to the x, all right? But it's not the case. What do we do in this case? So, well, whenever we have an exponential like e to the x plus or minus an e to the negative x, how about we get rid of the negative exponential? I mean, how do we get rid of it? Because I mean, subtracting it from both sides, it's not going to do that. All right? Well, in this case, we can do some operations such that these exponents get canceled and become a 0, and that exponential to the negative x just goes away. Well, how about we introduce some exponential? Yes. Oh, you were just stretching? Oh, that's fine. So, well, the trick here is to do the opposite of e to the negative. It's sort of the opposite. Well, not the opposite. It's actually the opposite exponent, because the opposite would be having a negative in the front. And no, that's not going to cancel. In fact, it's going to make it negative on the right hand side. So I'm going to multiply by e to the x on both sides. Well, e to the x times e to the x, isn't that e to the 2x? And what about, you know what, let me do one step at a time so you can see the whole thing. So that's e to the x times itself, e to the x, plus e to the x times e to the negative x equals 6e to the x. Well, so we have the same base, and so that means we can use laws of exponents. That is a to the m, a to the n, add the exponents, e to the x plus e to the x minus x, and here is where that exponential is just going to go. Plus 6e to the x. That's going to become e to the 2x plus e to the 0 equal, oh no, that's not a plus, that's an equal sign, and 6e to the x. And well, that negative exponent is gone. So because e to the 0 will be simply 1, and e to the 2x equals 6e to the x. And I think you guys can see where are we heading to with this problem. So we're going to move this 6e to the x to the left hand side with the opposite sign, e to the 2x minus 6e to the x plus 1 equals to 0. So, and I think we can see that quadratic pattern, isn't it? Because we have this e to the 2x, e to the x, and then essentially e to the 0x. We have the pattern 2, 1, 0, like in any other quadratic equation. Something like, x squared plus 5x plus 3. So even though that 3 is just a number, well, there's an x in spirit. Let's summon its spirit. It's essentially x to the 0 power, right? We have descending powers. Same thing here with exponentials. And let's see. Okay, so again, I'm going to rewrite this e to the x. Yes, I'm going to go about here. E to the x quantity squared minus 6 times e to the x plus 1. So now that we identified this quadratic pattern, so we are essentially done working in the world of x because there's nothing else we can do in the world of x. So let's go to the world of u. And the world of u will be u equals e to the x. And, same color here. So let me go over here. Let me continue here. I'm going to rewrite an equation, u squared minus 6u plus 1, which we can solve in a lot easier way than the equation that we end up with in the world of x. All right, and here is where we look at every possible solution technique for quadratic equations. And well, factoring is not going to work definitely because, well, factors of 1 that add up to -6, there's definitely none of them. Because the only factors of 1 are -1 times -1 or 1 times 1. In none of the cases we get a -6 as an addition. So completing the square perhaps, no, that's kind of madness. I mean, it's a fun thing to do, but no, I don't want to do that. So quadratic equation or quadratic formula would be a good way to go about it. However,